Okay, question number 38. We are continuing on in Chemistry 1401 with the final exam review. And the question says, when 68 joules of energy are added to a sample of gallium that is initially at 25 degrees Celsius, the temperature goes up from 25 to 38 degrees Celsius. What is the volume of the sample? Well, we're given the amount of heat energy added to the sample, and we're also given the change in temperature. Now we're asked to find the volume of a sample, and the information that they've given us is they've given us the specific heat, C, and they've also given us the density, right, D. Well, this question kind of involves connecting two formulas, right? Because we know the equation Q is equal to M mass times C specific heat times delta T. There we go. Now we can figure out delta T. We have been given C and we've also been given Q, so we can solve for M. If we have the mass of a sample and we have its density, surely we can solve for its volume using density is equal to mass over volume and rearranging that to volume is equal to mass over density. So let's start by solving for the mass of this sample. So we're going to say Q is equal to mass times specific heat times delta T. Therefore, mass is going to be equal to Q, the heat, divided by C times delta T. That's going to be equal to 68.00 joules divided by our C, 0.372 joules per gram degrees Celsius. Our delta T is going to be our, remember, delta T is equal to TF minus T initial. So that's 38.0 degrees Celsius minus 25.0 degrees Celsius, 13 degrees Celsius. And look at our units. We see that degrees Celsius cancel, as do joules, and we're left over with our mass and the units of grams. When I put that into my calculator, I should end up with 3 significant figures, and I end up with a mass of 14.1 grams. Now we can use the formula density is equal to mass over volume, and we can rearrange that to solve for volume. Volume is equal to mass over density. So I plug in my mass, which is 14.1 grams, and I divide it by the density of gallium, which is 5.904 grams per centimeter cubed. You see that the units of mass cancel, and we're left over with the units of centimeters cubed. Looks good. So when we divide 14.1 by 5.904, we should have 3 significant figures because of our numerator, which has 3, and we end up with 2.38 grams per centimeter cubed as being our final answer. Question 39 deals with change in enthalpy. It asks us to calculate the change in enthalpy for the following chemical reaction using only bond energies. All right, and hopefully you remember that delta H of a reaction when we use bond energies is equal to the sum of the bond energies of bonds that are broken. Bonds, maybe I'll just put broken. Make it simple. Broken minus the sum of the bond energies of the formed bonds. All right, so then we just have to analyze the equation, or the reaction here, which is Cl2 plus F2 produces 2 molecules of ClF. Everything's in the gaseous phase. Well, what are the bonds that I'm breaking? If I take my delta H of my reaction, I'm breaking the bond in Cl2. So I know that's worth 243 kilojoules per mole. I'm breaking the fluorine bond, which is worth 159 kilojoules per mole. So that's the total of my bonds broken. And then I'm going to subtract the sum of the bond energies of the bonds that are formed. Now, here it has the value of bond energy of a chlorine-fluorine bond, but I'm forming 2 molecules with that bond. And so I'm going to subtract 2 times negative 255 kilojoules per mole. There we go. Now I have to just punch all that spinach into my calculator. When I simplify this, I end up with the delta H of my reaction as being equal to 402 minus 510. Remember, our units are kilojoules per mole. And this is an exothermic reaction because our delta H is negative. And we end up with negative 108 kilojoules per mole. Now, another way of phrasing this equation here is we say that the delta H of the reaction is equal to the delta H's of the reactants minus products. All right, so we look at the delta H's of the bond energies of the reactants minus products. Now, broken, and those are obviously the reactants. But if you think about the delta H of formations, because we also looked at questions where we calculate the delta H of reaction, but instead of being given bond energies, we're given heats of formation. And when we're given those, it's the opposite. It's products minus reactants. Let me show you. Question number 40. The combustion of ammonia is represented by this equation right here, perfectly balanced out for us. And they also give us the delta H naught of the reaction. Exothermic reaction. We do this reaction, we give off 904.8 kilojoules. Okay. It says, what's the enthalpy of formation? So what we're looking for is the delta H of formation of ammonia gas is equal to what? Given that the enthalpy of formation of nitrogen monoxide is 90.4 kilojoules per mole, and the enthalpy of formation of water is negative 241.8 kilojoules per mole. Let's write those in. So above the NO, I'm going to write 90.4 kilojoules per mole. And then above the water, I'm going to write negative 241. It's kind of tight here. Negative 241.8 kilojoules per mole. Now, we're looking for the delta H of formation of ammonia, aren't we? Notice that they haven't given us the delta H of formation of O2, right? The reason why is because the delta H of formation of O2 in the gaseous state is 0, right? Because O2 is the standard state of oxygen. All right, whenever we have anything in its standard state, it's going to have a delta H of formation of 0. Now we're going to use our equation. This is what I was getting at before I switched slides. I said the delta H of reaction when we're using heats of formation is going to be equal to the sum of the stoichiometric coefficients multiplied by the delta H of formation of the products minus the sum of the stoichiometric coefficients multiplied by the delta H of formations of the reactants. All right. And the reason why reactants and products are flipped when we use heats of formation versus bond energies is, right, heat of formation, that's talking about forming bonds. Whereas bond energies are the amount of energy associated with breaking bonds. So since they're opposites, kind of opposites, this is why we end up switching these values here. All right, anyhow, so this is an equation that you need to familiarize yourself with for the final exam. Well, let's plug in some numbers. We know that the delta H of our reaction is negative 904.8 kilojoules per mole, and that's going to be equal to 5 times 0, so I'm going to leave that out. Completely erratic, starting off with the reactants, aren't I? I'm supposed to start off with the products. Okay, there we go. So 4 times 90.4 kilojoules per mole plus 6 times negative 241.8 kilojoules per mole. So that takes care of our products. And then we're going to subtract 4 times X. We'll call it X, and that'll be our heat of formation of our ammonia. All right, so subtract 4X. Okay, so now it's just a matter of doing a little bit of algebra, right? Nothing more than that. So I've gone ahead and simplified this quite a bit. And when you do, you end up with negative 904.8 kilojoules per mole is equal to negative 1089.2, oops, forgetting my units, kilojoules per mole. Subtract 4x. I'm sure everybody here can solve for 4x. 4x is equal to negative 184 kilojoules per mole. And then we get the x is equal to negative 46.1 kilojoules per mole. All right. Just a little bit of algebra and knowing this formula here, knowing how to calculate the change in enthalpy for a reaction when you're given pizza formation. All right, there we go. That's one that everybody move on to the next one, which deals with Hess's law. So we're still on the theme of enthalpy. Given these values for delta H of these three reactions here, three beautiful reactions, we want to calculate the delta H for this reaction, right? And we can calculate that delta H for that reaction even without having done that reaction, right? As long as we can manipulate these reactions, these three reactions, and add or tally them up in such a way that we end up overall with the resultant equation that I have highlighted in yellow. Well, the first thing I noticed about that equation that I have highlighted in yellow is that it's got one molecule of carbon disulfide in it, and the only place that I see carbon disulfide is in equation number 1, and there's 1 mole of it. So I'm going to call these equations 1, 2, and 3. I don't need to manipulate equation 1 at all. So I'm not going to change that one bit. So let's just put equation 1. Let's rewrite it. So it's carbon disulfide in the liquid phase plus 3 moles of oxygen produces carbon dioxide and 2 moles of sulfur dioxide. And let's leave we'll put delta H here at the top. And what's the delta H is negative 1077 units of kilojoules per mole. Okay, so that's the first one. What else do I see here? Something else that I notice is that I have 6 moles of water as a reactant. The only place I see water in any of these equations is right here, right? I have 1 mole as a product in reaction number 3. Now, if I want it as a reactant, I'm going to have to multiply that by a negative factor, right? That's going to reverse everything, and it's going to change this sign from positive to negative. But I need 6 moles of it, so I'm going to multiply it by a total of -6. So I'm going to take reaction 3, I've multiplied it by -6, then I'm going to have 6 moles of water produces 6 moles of hydrogen gas plus 3 moles of oxygen gas. And when I multiply 286, oh, sorry, Mr. Deon can't see very well, can he? Sorry, you guys, I'm not kidding. I need a new prescription pretty bad. I have an appointment next week. So when I looked at this, I saw H2O. When the H2O is over here, so I don't multiply that by -6. I'm just going to multiply it by 6. My mistake. Sorry, guys. Nobody stopped me. All right. Somebody stopped me. There we go. Okay, I'll just fix that. There we go. So I have 6 moles of water. That's better. Sorry, no. Jeepers, I can't see. 6 moles of what? H2. Shoot. 6 moles of hydrogen plus 3 moles of oxygen produces 6 moles of water. So I multiply -286 times 6. I've already gone ahead and done that. And you end up with -1716. Okay, and then what's the last thing we got to do? Is we got to do something with equation number 2. Let's see here. Well, equation number 2 has the hydrogen peroxide, doesn't it? Right, but there's only 1 mole as a product, and I need 6 moles as a reactant. So that one I'll multiply by -6, won't I? -6. So that will give us, let's see here, that'll give us 6 moles of H2O2, and it will produce 6 moles of hydrogen plus 6 moles of oxygen, and that'll give us a delta H of 1128. So when I tally up these three equations, right, I should get a few things canceling. Well, you can see that I have the 6 moles of hydrogen on both sides. If you tally these two oxygens up, right, you get a total of 6 moles of oxygen, and then I have 6 moles of oxygen over here. What else cancels? I guess that's it. And that's everything that cancels out. So if we add this all up together, what do we get? Carbon disulfide, plus 6 moles of hydrogen peroxide, produces carbon dioxide, 6 moles of water, and 2 moles of sulfur dioxide. So everything works out. Now I just have to tally up these three numbers here to figure out the delta H of reaction. And when I do that, I get the delta H naught for this specific reaction is being equal to negative 1,665 kilojoules. Okay, so there we go. So carbon disulfide, I just want to double check it here, plus 6 moles of H2O2 gives you carbon dioxide, yes, plus 6 moles of water, states of matter, 2 moles of sulfur dioxide. Yep, looks good to me. There we go. So that means our delta H of reaction is negative 1665, and there you have it. Give me a thumbs up if you think you can apply Hess's law. Usually students are pretty good with Hess's law. All right. There we go. Okay, question number 42 deals with oxidation and reduction. You will remember the acronym that we use, oil rig, right? So oil stands for oxidation, is losing electrons, and rig stands for reduction, is gaining electrons. All right, let me rewrite the equation here because it's pretty small. So if we have iron plus a copper 2 plus ion produces copper and an iron 2 plus ion, like that. Well, what's happening here? You can see that iron is going from a charge of 0, no charge, to having a 2 plus charge. Therefore, the iron is undergoing oxidation, right? Whereas the copper is 2 plus, it's going from copper 2 plus to copper 0. Well, how do you lose 2 plus charges, right? You have to balance them out with 2 negative charges. So it's gaining electrons, and so it is being reduced. If you look at the possible answers, it's saying, which statement is true? We're looking for a true statement here. Copper is being oxidized. The copper ion, no, it's being reduced. The metallic iron is the reducing agent. That's true, right? Because the copper is undergoing reduction, right? It's going from copper 2 plus to copper 0. Okay, but what's causing the reduction? The iron is causing the reduction. If you look at all the other ones, they're all messed up too. The metallic iron is reduced. No, it's oxidized. And the copper ion is the reducing agent. No, the copper ion is being reduced. Okay, so there you have it. All right, so a little bit of redox, a little bit of oxidation reduction. Question 43, which of these has the smallest atomic radius? Bromine, fluorine, chlorine, and iodine. Well, these are the halogens, and you would remember that the halogens come in this order: fluorine, chlorine, bromine, and iodine, like that. And we know that as we go up a group, or as we go across a period from left to right, the atomic size decreases. Okay, fluorine's a really small element. We know that, right? Fluorine is a really small element. It's got a high effective nuclear charge, pulls its electrons in really tightly. So fluorine is definitely the smallest out of all these. So knowing a little bit about atomic trends, what's the next one? What happens when a bromine atom becomes a bromide? All kinds of things. You throw a little party for it. So you take a bromine and it becomes a bromide, right? It means that the bromine must have gained an electron, right? So you could write it out like this: bromine plus an electron gives you bromide. So the bromine nucleus acquires a negative charge. It's got nothing to do with the nucleus. If you change the nucleus, then you change the identity of an atom, so that's wrong. the atomic number of the bromine is decreased by 1. Well, the atomic number is the number of protons, right? So that's not going to change. The bromide ion is larger than the bromine. Yeah, absolutely. We know that as you increase the number of electrons and the number of protons in the nucleus stays the same, they're not going to be held as tightly. And so the bromide ion is going to be larger than the bromine atom. So this one is true. And it says a positive ion is formed. Well, that's just out in left field because you're adding an electron, right? You should know that a bromide is Br minus. Think about I, right? Sulfide, oxide, nitride, phosphide, so on and so forth. Carbide, right? Those are negatively charged in chemistry. Okay, let's move on to question number 45. Which of these elements has the highest electronegativity? I say in life there are few absolutes: death, taxes, and electronegativity. Students love electronegativity, and they all know that fluorine is the most electronegative atom in the periodic table, right? We'll say fluorine is most electronegative because electronegativity increases as you go up a group and as you go from left to right across a period. Okay, well, if we look at these atoms here, you have cesium, which is way the hell down here. Cesium is actually the least electronegative element on the periodic table. Then you got lithium that's over here. You have iodine, which should be down here below fluorine, but then you have oxygen, which is really close to fluorine. In fact, oxygen, as I've told you several times, it gets second place, right? Second most electronegative element in the periodic table. And so the winner is oxygen. So you should know the trend for electronegativity. Question 46. The first three ionization energies of element X are, so if we list off our ionization energies, okay, IEs, you've got first, second, third. So the first one is 590 kilojoules per mole. Then the next one is 1145 kilojoules per mole. And then the next one is 4,912 kilojoules per mole. Well, you can see what's going on here, right? When you go from the first to the second, there's a jump, about twice as much. But then when you go from the second to the third, you have a huge change, right? You have more than 4 times as much. And so that tells you that these 2 electrons here, these are valence electrons, right? They don't take nearly as much energy to remove as this electron here, which is a core electron. Okay, so that tells you that this atom, or this element, has 2 valence electrons. Now it says, what is the most likely formula for the stable ion of X? If it's got 2 valence electrons, it would want to lose those 2 valence electrons, right? Because core electrons, generally speaking, atoms don't want to lose core electrons. If you lose 2 electrons, if you take element X and then it loses 2 electrons, what are you going to be left over? You're going to be left with a 2+ ion. And so X2+ would be the ion of this element. Number 47, kind of a fun question. It asks us, which procedure can be used to demonstrate experimentally that this reaction obeys the law of conservation of matter, right? You can't create and you can't destroy matter during a chemical reaction. Okay, now you got to read these carefully. But remember, it's asking you, which procedure can be used to demonstrate this. Like, look, before we even read the answers here, if we look at the reaction, you're taking magnesium and you're burning it in the presence of oxygen. I'm sure that many of you have done that, right? In the chemistry lab, in the wet lab, you take magnesium, heat it in a flame long enough, and you get this bright flame. It's so bright, so intense, you can't even look at it. And you form mag oxide, magnesium oxide, which is a white solid crust, or just a solid powder. Okay? Now, if you take the magnesium and you just burn it in the presence of oxygen, like in the air, that doesn't prove the law of conservation of matter, right? Because a knee-jerk reaction would be to say, okay, I'll just take the magnesium, I'll react it in air, right? It combines with oxygen, then I get magnesium oxide. I have my number of moles of magnesium, and it's only going to react with a certain number of moles of oxygen, right? 1 mole of oxygen for every 2 moles of magnesium. There we go. I can use the law of conservation of matter. That doesn't demonstrate the law of conservation of matter. right? It's not a good way to do it because it doesn't prove that. What's the way I could phrase this? It doesn't prove the fact that matter was neither created nor destroyed. Right? It doesn't, in fact, prove that because you don't know, well, how much oxygen did it react with if you're talking to somebody who doesn't understand, anything about moles. So let's take a look at these answers. It says take a mass of 1 point something grams of magnesium, burn it in pure oxygen, then compare the mass. That's what I just said. That's not a way to represent the law of conservation of mass because you don't know how much oxygen you started out with. The next one says determine the mass of a sealed flash bulb. So that's kind of like, just a bulb that's closed, containing magnesium and oxygen. Ignite the mixture, cool it, and compare the final mass of the bulb plus the contents with the original mass of the bulb plus the contents. So look, what you're doing is you're taking some kind of bulb, which would look like what? I don't know, it could look like a lot of different things. But you got some kind of bulb like this, and then on that bulb, you'd have a stopcock. Okay, so you'd have some way of closing it like this. Okay, now inside there, all you have is magnesium and oxygen. Okay, you got nothing but those two. Okay, then you ignite it. Okay, and you end up going from magnesium and oxygen, which had a certain mass associated with it, to magnesium oxide. And the idea is that the mass before is going to be equal to the mass after. That's what they're saying here. And that actually proves the law of conservation of matter. Why? Because you did a chemical reaction, right? You made a bond, an ionic bond between the magnesium and the oxygen, but nothing was created and nothing was destroyed, right? You started out with a certain amount and you ended up with a certain amount. Okay, so that actually proves the law of conservation of matter. Okay, let's just look at the last ones. Show that the sum of the two atomic molar masses plus one molecular mass, that's got nothing to do with the law of conservation of mass. Okay, that does not show it experimentally. Sorry, I shouldn't say it doesn't have anything to do with it. It doesn't prove it experimentally. It does represent the law of conservation of mass, but not experimentally. And then the last one is you burn a gram of magnesium in a tall beaker filled with air, scrape out the mag oxide. That's the same thing as this, right? It doesn't prove that you conserved all the oxygen that was reacted, right? It doesn't prove that at all. Okay, and so the best answer is the second one. Let's move on to question number 48. The orbital diagram represents the correct valence shell ground state for, so we've got 3d5. Okay, so whatever we have here is going to be argon 3d5, like this. Now, what are the possibilities for argon 3d5? Let's look at all these. If we have magnesium, or sorry, manganese 2+, manganese is element number 25. Let's go to the second one. Manganese has an electron configuration of argon 4s2 3d5. So if you go from manganese to manganese 2+, remember the first in, first out rule. You're going to lose these two electrons, and you're going to end up with argon 3d5. So that must be the correct answer. Let's see what's wrong with the iron and the iron 2+. Iron is element number 26. If I look at the electron config of iron, it's argon 4s2 3d6, like this. If I lose 2 electrons, I end up with argon 3d6 according to the first in, first out rule. And so the answer for having just the 5 3d electrons would be the manganese 2+ cation. Question number 49, I don't like to use this word simple in chemistry, but I'd say it maybe a less complicated question, as long as you understand what a sigma bond and a pi bond is. Remember, the first bond between any two elements is a sigma bond, right? This is a sigma bond, this is sigma, this is sigma, this is sigma, this is, oh boy, I'm really into it here. Now I'm kind of stuck. I have to label them all, right? This is a sigma, this is a, right? This is one, here's another, and there's one right there. Now, how many sigma bonds do I have total? I'm just going to erase all that, okay? So let's erase all that, delete. Let me use a highlighter. Look, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then every double bond has one sigma bond. So 11, 12, 13, 14. So I've got 14 sigma. So it must be this. It's the only possibility. And pi bonds. When I have a double bond, right? Let's say you have a double bond, right? The first bond is sigma. The second bond is a pi bond. And so how many pi bonds do I have? Let's see. What should I have? I should have 4, right? 1, 2, 3, 4. Looks good to me. So 14 sigma and 4 pi. Just one more thing before we move on. Remember that when you have a triple bond, and this is something we went over a few times, right? First bond is a sigma. Everything after a sigma is a pi. So you've got 2 pi bonds in a triple bond. Capiche, capoche? All right, let's look at the very last question on the practice exam. After that, it's just a blank page. What's the formal charge on the carbon of the carbonate ion? Right, this is kind of, if you take a lower level chemistry class, you know, something below chemistry 1401, they might ask you to draw Lewis structures, and then they don't teach you how to assign formal charge, and they'll just put brackets, and you say, well, overall, there's a 2 minus charge. Because if you look at every element in here, the 3 oxygens, they all have an octet, right? The carbon has an octet. Everybody's happy. But what's the formal charge? Well, formal charge is equal to the number of valence electrons subtract sticks, subtract dots, right? So for the carbon, it's got 4 valence electrons. Carbon's in group 4A. It's surrounded by 4 sticks and 0 dots. So the formal charge of the carbon is going to be 0. And there you have it, right? Where do the formal charges come from? They come from these 2 oxygens here, right? Because oxygen has 6 valence electrons, subtract 6 dots and 1 stick. That gives you -1. So I have a -1 here. I have a -1 here. And this oxygen here, which has 2 bonds and 2 lone pairs, you have 6 minus 2 sticks and 4 dots, which also gives you 0. So formal charge, make sure you know how to calculate formal charge. And that is the end of the practice final exam.